Okay, so far we have seen how to use a MOS structure as a capacitor. We will now go ahead and see how to make it into a transistor. Remember we talked about bipolar transistor before, where the field was created by the PN junction and the external applied voltages. Now we'll see how to use the MOS structure as a transistor. So we're familiar with this MOS capacitor. We just seen some time back in the previous video, where the gate is insulated from the semiconductor through an oxide, and to increase the minority carriers supply we put the opposite type polarity as a substrate. So in this case it's a p-type substrate, so we put a n-type material here so that it can give you excess electrons easily. So then you get a very good gap between the gate and the channel which is formed here, and the channel is contacted through the n-type material, and VGB is greater than VTH for inversion to happen. So you've seen this in the previous video, and this was the MOS capacitor. Okay. The substrate is grounded, and you got a capacitor between these two terminals. Remember, the substrate, all these things are now the capacitor is between the gate and the n-type material which has been put here. Okay. And they are connected through this. Now the channel itself is resistive because it is just a, between these two types, it's just a resistor. It's got a free electron concentration gradient here, free electron charge here, and that causes a resistance between this type and this p-type and n-type. Though they are externally shorted right now, okay, but through the channel there is a resistor. So if these are not shorted externally, can this resistor be used? That is the question. Okay. So let's say we ground this other terminal as well, right? And you bias the one side of the new contact that we have put in through a VD. Let's say we increase the potential of this side relative to this side and apply a positive potential VD. Now we know there's a resistor here. So what should happen ideally? You will have a current flowing through this, right? Because of this excess VD that you have put in here. Okay. So since you put in a positive voltage here, electrons will go from here to this side and they constitute a current. Right? And they constitute a current in the opposite direction, in this direction, opposite to the flow of electrons. This n-type is now called a source because it is sourcing the electron. The electron, remember, went through like this. Right? So this is sourcing the electrons, so it's called the source, sourcing the minority carriers, or what you call the majority carrier in the inversion region. So it is sourcing the electrons in this case, so it is called the source. This is called the drain because it's draining the electron from the channel. Right? And this itself is the channel. The inversion region is called the channel because that's the electron from the source enters the channel and goes to the drain and then goes like this. In effect, the current goes in the opposite direction. Now what happens if we increase VD? If we increase VD, the field across this channel increases. So this field increases, you know, the velocity of the minority of the charge increases. So the electron will go now faster. Right? What does a faster flow of electron mean? A faster flow of electron means the electron goes through a particular area given a point more number of times. Right? So it means more current. More electric field means more velocity means more current. So the current increases. Now what happens on the other hand if we increase VGB? We had set it in the previous example at a point above the threshold, but now let's say we increase it further. When we increase it further, the inversion layer charge increases. We've seen this before. The amount of free electrons here increases. Right? So now there will be more number of electrons flowing for the same potential. It's not that the speed has increased, it's not that the field has increased, hence the velocity hasn't changed, average drift velocity hasn't changed, but the number of free carriers, the number of electrons in this case flowing through increases because we increased VGB, which increases the amount of free electrons out here. So this increased number of electrons going through also constitutes an increased current. Right? So increasing VD increase current, increase VGB also increase current for us. Okay. What happens when we reduce the gate to bulk voltage less than the VTH? Okay. When you reduce less than the VTH, there is no inversion region formed here. There's just a depletion region. Hence, no current flows. Okay. There's no free electrons here. There's no channel. There's no channel of free electrons sitting out here. Only depletion region is sitting here. Only when the field increases a lot to break down this material will there be any current, just like in a reverse bias diode. But that's not the case we are talking about. Let's say VDs are not such high that breakdowns occur. There will be no current from source to drain this time. No electrons flow from the source to drain, hence no current from drain to source. This is called the gate. It's called the gate because you can see it controls the flow of current from source to drain. So if it is not large enough, it cuts the current. Above a certain value, it lets the current flow through. And this is called as substrate or bulk, because this is on which the entire structure is built, just like the capacitor. Okay. So let's look at some cross section. Okay. So we had the bulk type, you had the gate oxide just growing on it. Then we have the gate material deposited on it, which is typically a polysilicon or metal. Then you have the source drain implants done here. These were the majority carriers in the channel suppliers, right? So source and the drain. In this case, since the bulk is P-type, you make it N-type here. Okay. And the channel is just formed below the oxide near the surface of the bulk, but not in the source drain, because this is slightly dropped compared to this, and this is the opposite polarity anyway. So the inversion happens here, the green thing that we see out here. Right? That is called the channel. Okay. The distance from the drain to source is called the length of the channel, because that's what the length of the channel is. Right? You can see the channel is formed here. This is defined by the length of the gate. The width of the gate defines how much cross section we get. So this is the width. Right? Because it's perpendicular to the flow of current. L is in the flow of current. W is perpendicular to the flow of current. And then there is Tox, which is the oxide thickness. These are the key physical dimensions of a MOS transistor. Right? The width, the length, and the Tox. Tox is in the vertical dimension. Length is in the direction of the current flow. And W is perpendicular to the dimension of the current flow. Okay? This is for an NMOS transistor. Same thing for a PMOS transistor. You start with instead of a P-type bulk, you start with an N-type substrate or N-type bulk. Right? And instead of N plus diffusions here, you put it as P plus. The source and drain is made of P plus, because the inversion channel, because it's N-type here, the inversion channel will be of holes, and you have to have excess holes to be supplied or drained, which is done by the P plus. Right? The rest of the things remain same. This is a PMOS transistor. Right? W is called the width of the channel or the gate. L is called the length of the channel, and Tox is the gate oxide thickness. Right? The W and L are under designer's control, because you can choose the W of the transistor, you can choose the L of the transistor. But Tox is actually process fixed. The oxide thickness is determined by the process, and you don't have any the designer doesn't have a control on this. Once the transistor is designed in the process fab, the Tox remains fixed for a particular kind of transistor. Of course, in every process you'll have different flavors of transistor which might have different Tox, but for a given flavor of transistor, the Tox is fixed. In those, you can play with the W and L to do your design. So let's look at the MOS drain current. What is the effect on the drain current? So when you saw that the VGS increased, the amount of channel charge increased. If the amount of channel charge increased, current increases. Right? Because there are more number of free electrons available, the current increases. So ID is proportional to VGS. VDS, when VDS increases, the drift velocity increased. Because the field increased, the drift velocity increased, which also increases ID. So ID is also proportional to VDS. If width increases, ID will increase because there is more cross-sectional area. Right? The amount of Q inversion increases because the width does increase in fact. Right? So ID is proportional to W. If length increases, on the other hand, the field reduces because the length has increased. The potential is now dropped across a larger length. So the field is reduced. So Vd, the drift velocity reduces. The drift velocity reduces, current increases. So ID is proportional to 1 by L. Okay. What happens if Tox increases? This is a dimension, right? These were voltages and these are dimensions. So if Tox is increased, Q inversion actually reduces because the gate has lesser control on it. The field actually drops across the oxide, and which is now thicker. So there's less potential for the inversion to happen. So Q inversion decreases, so ID reduces. So in a way, ID is proportional to the inverse of Tox. So if Tox increases, ID reduces. Okay. So let's take a MOS in a linear region. There's a gate, the N plus drain and N plus source, P-type substrate bulk which is grounded. Let's say it's grounded. Right? And now I'm making a slight shift. I'm going to supply the gate relative to the source. I'm going to call that VGS. Okay. You know the length of the transistor, length of the channel is called L. And when the VGS is above VT, you get a channel. Right? You do get a depletion region both below the channel, which is because of the gate applied voltage, as well as from the reverse biased diodes out here. So these areas which you see here are because of these areas that we see here are because of the diodes, the reverse biased diodes. Right? This is from the source and this is from the drain, and these areas here are because of the gate. This reverse biased diode, the depletion regions here are because of the gate. And to this now we apply a source voltage also, a drain voltage relative to the source. It's called VDS. Okay. When you do this, right, if you look at the junction here, this is where the electrons will now flow out, right? So we'll just use this as a point of observation. Current is nothing but rate of flow of charge that we have seen, right? So the velocity is nothing but when the voltage VDS is small for low VDS, velocity we have seen before is proportional to the electric field applied. So it's mu times E. And what is the electric field? L. VDS is applied across a distance L, so it's mu times VDS by L. And this holds good for low VDS. There's no saturation, right? So drift velocity is directly proportional to E. E is nothing but VDS by L. So velocity is mu VDS by L. What does that mean? Right? So if you consider all the electrons, all the free charges, which are at a distance V meters, though it's called meters, it's usually be a few microns, but because the units are meters, I'm going to call it in meters. So at V meters from the drain would have crossed this position in 1 second. That's what V means, right? So electron from here definitely will cross. Electron from here will cross. Electron from here definitely cross in a second. The electron which is V meters away from it would definitely cross this in 1 second. The one which is slightly away from it will not be able to cross this in that second. So all the electron in this darker green region will cross this junction in 1 second. And how much is the charge? Right? Amount of charge per unit area, which is Q and V, right? Into the width into V, right? Because this gives you the area. Width is the cross perpendicular dimension as we saw in the previous part. Right? So this is the width into V, which is the cross section area, which would have crossed this junction, this area, right? Into the charge per unit area, and is negative because it is an electron charge here, right? QINV is the unit per charge. So QINV now is nothing but minus Cox VGS minus VT. Minus because it is the electron charge here. So Cox into the excess voltage above the threshold voltage that has been applied. You've seen this from the capacitor as well. Right? So we just go substitute it back. ID is nothing but, I'm substituting for velocity mu VDS by L. QINV I'll substitute from here. So you will get it mu Cox W by L VGS minus VT into VDS. Right? You can see it's proportional to VDS for small VDS. It is also proportional to VGS minus VT. Right? It's proportional to W, inversely proportional to L, and proportional to Cox, which is inversely proportional to Tox. This is what we saw in the previous slide. This is the current in the linear region. Now what happens as we increase the voltage a little bit? This was at very small VDS. Now let's say we let's increase the VDS a little bit, right? What will happen is the amount of charge in the inversion region near the drain actually reduces because the drain voltage has increased. So in effect, you can see gate to drain voltage, this voltage here actually drops. So then lesser amount of inversion region here, right? So you'll get a linear gradient of the inversion region. So now how do we calculate? Previously it was easy because the charge was uniform. You could have just taken V and multiplied, you got the total amount of charge crossing this junction in a second. But now it is not uniform. It is linearly grading out. Right? It's still not a very large value of VDS, but the charge is not uniform, so hence we have to resort to a different technique of calculating. We'll see what it is. Right? The voltage is not same along, hence this happens, right? So what we will do is we'll just take a small region of the channel. So instead of taking the full length, we'll call it dy and calculate the amount of charge in here. Right? The voltage at this position, let it be Vs plus Vc, where Vs is the source voltage. Vc varies from 0 to VDS because this is at VD and this is at VC, 0. So this will be Vs plus VDS, this is the VD. Right? So Vc varies from 0 to VDS. Right? The channel voltage is Vs plus Vc. Right? So when this happens, we saw the linear region equation current. The current has to be constant everywhere. If the current is not constant, charge will build up in a particular area. And that is not the case. Let's say it's an equilibrium. There's no charge built up. It's in steady state. So whatever current flows through flows through everywhere. Right? So the current in this small junction in this small area is ID is mu Cox W by L VGS minus VT into VDS. This is the equation for a linear region MOS transistor when VDS is small, very small. I'm going to use this equation and apply it to the small area. Right? So mu Cox remains the same, width is the same, but the length we are considering is only dy now. Right? So length is replaced by dy. Right? VGS minus Vs minus Vc minus Vt. Because VGS is nothing but Vg minus the voltage at this point. But the voltage at this point is Vs minus Vs plus Vc. Right? So Vg minus Vs plus Vc, which is Vg minus Vs minus Vc, in excess of Vt, so minus Vt, that is done. And what is the voltage drop across this? We'll call it dVc. Right? That's a small change. There's a drop across this small region. Right? The absolute potential is Vc. Let the drop in the potential across the small region by dVc. So VDS is replaced by dVc. So this is the current. Right? Right? This is what I'm explaining right now. Right? So I into dy, I'm just taking the dy this side, is mu Cox W VGS minus Vs minus Vc minus Vt dVc. Right? Now if I integrate both sides from 0 to L, dy actually varies from 0 to L. Right? The voltage varies when dy varies from 0 to L, the voltage dVc varies from 0 to VDS. That's what we saw here, right? 0 to VDS. So integral 0 to L I dy is nothing but 0 to VDS of this expression. And that turns out to be, you can work that out yourself, mu Cox W by L VGS minus Vt into VDS minus VDS square by 2. Right? So you see a small correction term here, minus VDS square by 2. Rest of the equation is the same. So as you increase the drain voltage, the current tends to reduce. It doesn't increase as much. So I shouldn't say reduce. It doesn't increase linearly at VDS. It does increase, but there is a subtracting term also, which is VDS square by 2. So it doesn't increase as much as this first part of the equation says. It does increase, but the rate of increase reduces. Okay. So this is the actual equation for a linear region MOS transistor current. So in the first case, when VDS was very small, the VDS square can be neglected and you ended up with this equation. Okay, is that clear? Now, what happens in this case we increase VDS even further. Right? We already started with a case where it was the charge was linearly varying from source to drain, charge per unit area. Now if we increase VDS even further, at some point, right, at some point the channel will pinch at this position. When that happens, because the VDS has increased, you also saw that the depletion region charge below the drain actually ends up increasing. Was this also the reverse bias diode, right? So that increased, the channel actually got pinched off here. Right? When that happens, VDS is equal to VGS minus VT. And under this condition, okay, this actually starts to pinch off here. Okay? Because the surface here is actually very close to the threshold. So at the limit, when that's exactly equal, this surface is not even inverted at that point, just beginning to invert, right? And then it's a linear gradation here. So ID in this case, this is what we calculated in the previous case, where for a non-small VDS, now all you have to do is substitute VDS equal to VGS minus VT. At this point, what happens? When you do this, when you substitute VDS equal to VGS minus VT in this equation, you'll end up with mu Cox W by 2L VGS minus VT the whole square. This is the saturation current, the famous square law that we get, right? Now if you increase further, the channel actually reduces further. Does it mean there's no current? No, there is a huge field here. All the field actually gets dropped across this drain to source. The excess field that we are talking about actually gets dropped from the drain to this position, not to the full source, the excess voltage, right? So all the channel that comes here because of drift will reach here, right? But what effectively happens is that the channel where it stops actually has now gone a little bit further in. What this effectively does is the length of the channel is now reduced. You can see that, right? Because across this is the voltage VDS, the VGS minus VT. VDS equal to VGS minus VT is dropped where this equation came, right? But the length is effectively dropped. The excess field as we increase VDS is actually dropped across this region, which is this depletion region, and that is the one that actually takes the currents through the magnetic area through drift action, right? So when the channel drifts further, reduces further, there is a 1 plus lambda VDS term comes in, which is effectively called channel length modulation because it comes because of the channel length getting modulated. So I'll retain the same L here, but add a factor called 1 plus lambda VDS. It's much easier to deal with this equation than modifying the L and knowing what the function of L is with respect to VDS. Okay, this is called a channel length modulation. So let's draw the characteristic, MOS characteristics. Okay. ID versus VDS. Okay. Let's say first we go above the threshold. We know below the threshold there's no current, and let's say we go 500 millivolts above. These are all old geometry transistors, so let's say 500 millivolts above. In the newer ones, you might have to do with 50 millivolts or even 10 millivolts, depending on the supply ranges. Right? So initially for small VDS, right, the current is linear, right? And for large, and then it tends to reduce as the VDS is trying to increase a little bit. Remember, we said it's not linear after some time. It is that VDS minus VDS square by 2 term starts coming in here. Okay? And then once it reaches saturation where the channel gets pinched off, the current doesn't increase too much, but it increases slightly linearly because of channel length modulation as the VDS keeps increasing. Right? Now if I increase the VGS to VT plus 1 volt, the current increases. The linear current itself increases, we saw that. Right? The VDS square then comes to reduce the rate of change of current, and then once it reaches VGS minus VT, now see this region, because VGS minus VT is larger, it moves out a little bit more. So VDS should be a little bit more larger. It's saturated here, this one saturates here, right? And then there is a VDS effect, which is the channel length modulation. This happens for various values of VT, right? You can see the jump in the current as you increase VGS by the same amount is not same because it is depending on VGS minus VT square here, right? So it keeps increasing, right? The jump in current at the same VDS for the same value of delta VGS is not the same. You can observe that as well. This slope, what we call, is because of the channel length modulation. Larger the VGS, more the channel length modulation effect you'll see. Okay. This point where the saturation occurred is exactly like the square law that we had before. Square law current. So beyond that, the current is constant, but depends only on the VGS, on the VDS by the channel length modulation. Okay. This region below this where the saturation occurred is called linear. Though in strict terms, these parts are still non-linear. It's still called the linear region because the channel is not pinched off. And once the channel is pinched off, it's called saturation. Okay. Unlike the bipolar transistor where the saturation happened when both the PN junctions were forward biased, right? This was called the forward active and this was called saturation there, right? Here it is called linear and saturation. This is now not from device physics. These terms are from designers now. You can see the current is kind of linear here with VGS, right? And with respect to VDS both. And hence it's called the linear region. Here the current is saturated except the channel length modulation. If we neglect that effect, the current is actually saturated, hence it's called the saturation region. Okay. Let's talk the ID versus VGS instead of VDS, and that we know is just a square law kind of thing, right? So below the VT, we know there is very little current, we call it cutoff. In fact, we'll call it zero current because it's so small. And above that, the square law holds. Of course, the square law has to be modified by 1 plus VGS, 1 plus lambda VDS. But let's say that lambda factor is small. It's just mu CX W by 2L VGS minus VT the whole square. Okay. So this in effect is the NMOS IV characteristics. PMOS will be similar except that VDS will be negative. ID will be from source to drain, right? Instead of from drain to source. Everything reverses. VGS will be negative as well. That you can check it out. PMOS is similar to the NMOS except for polarity reversal. We just talked about it. VT is negative. You have to understand this. You go have a discussion why VTP is negative. Right? For saturation region, VGS is less than VTP or mod VGS is greater than mod VTP. If you go the mod way, right, because these are negative values, so the sign changes. You go the mod way, the whole same old relations hold. Right? So if you want to understand PMOS, just take the modulus of the voltages and you'll start getting the same relationship as in NMOS transistor. Right? For linear region, VGS is less than VTP and mod of VDS is less than mod of VGS minus mod of VT. Right? So the current is due to holes. The current leaves the drain from the source to drain. Flow is from source to drain. Everything is just reversed. So you might want to have a small discussion or just sit through and think about the current directions and the polarity of the voltages for a PMOS.